representative composite structure, large area specimen.
So again, I'm Seth Kessler, and this is Eric Flynn from Metis Design. And today I'm going to be introducing the MD7 digital SHM system as applied to a complex composite sandwich panel part. This happens to be a part from the Sikorsky S-92 helicopter. There's two key elements to the system. The first is kind of hidden by this node, but that's our analog element, which is a guided wave beamforming sensor that's comprised of 7 deliberately placed piezoelectric elements. Over the sensor, we have our node, which we call the IntelliConnector. This is capable of facilitating guided wave testing, mole analysis, and acoustic emission. It's doing data acquisition, signal excitation, as well as it can do local computation along a digital bus. If you come around to the other side, I'll just show for the sake of the demo, we have our data accumulation hub back here, which is actually running the test and collecting all the data and statically storing it on an SD card. And then for this demo, we also have an off-the-shelf wireless card. So the data, after it's being stored, is being wirelessly transmitted to Eric's laptop over there that we're going to show on the visualization software. And the final piece I'll show down here is we have a battery that will run for about 24 hours or so. This demo running continuously, again, just to show a fully wire-free system. So if we can switch over now to the monitor. What I'm going to be demonstrating here again is first Eric is going to be loosening a bolt in the front here. Now the bolt that he's loosening is representing simulated damage here. We only have one of these panels, so we're going to at the end do some impact, but we're going to do some repeatable damage first. So he's going to loosen the bolt. Now this right now is running continuously. Our hub is commanding the network down the bus for each of these nodes to one by one send a 35 kilohertz signal and then collect it at 50 megahertz, or in this case 10 megahertz. We could run up to 50 megahertz. And then the data is being sequentially digitized at each of these nodes, then sent back through here, right into the hub, and then wirelessly transmitted up onto Eric's computer here. So again, Eric's going to, after it updates each of the nodes, so it's going one by one, the nodes update, and then the software is going to show the location. While we're waiting for that to update, I'll describe the second location. Eric's going to be unbolting this over here. There's 3 unique things about this bolt area over here. First of all, it's going to show multi-site damage because we have damage here and we'll have damage there. The second thing is that the damage is outside of the quote-unquote box. So we have 3 node locations. And this is actually outside typical systems that you probably see actually only look for damage inside of the formation. So we're going to be looking for it outside of the formation. And the final aspect of it is it's actually a very complex part where the nodes themselves are bonded on a part that is laminate with honeycomb core. And then, I don't know if you can see it, but we can show afterwards, it tapers down here. So there's ply drop-offs, taper, and then this bolt is actually just on a solid laminate, so there's no core in this region. So the waves are propagating across this boundary, reflecting off of this change, and then coming back up. And then again, it gets added up. So right now it's just showing the first location, and the second location will come up as soon as it revolves around. I should point out the slowest part of the system is actually the wireless transfer using the off-the-shelf part. It actually only takes a few seconds to collect the data and process it, and it probably takes about 30 seconds to do the transmission, which is just for this particular demo. As for the software itself, what you're looking at here is actually a 3D mesh that we've taken from ANSYS, and we're stitching our diagnostic results directly onto the 3D mesh. So what you're looking at, the color plot here, is the likelihood of damage map per node. So you can use this to facilitate prognostics via parametric finite element modeling. We can output this mesh with this likelihood map, and Eric could also impose, Eric, you can do some thresholding to show as we reduce the threshold levels, you can see that it goes, now it's being reduced so it gets larger area, you can pull it the other direction and have a more definitive point. But we're looking at this more of a probabilistic approach rather than looking at this from the point of view of a discrete point. So the final thing that I'm going to do is impact this, and I promise you this has never been rehearsed. This is only one panel that we have, so hopefully I'll be able to hit it hard enough to actually cause damage. Sorry to anyone in the front row that gets wet. So hopefully I cause damage and we see something interesting here, and then we'll talk about the rest of the system. Try that again. No nerves here. Okay. So I did more than scratch it, so that's good. So, okay, we should be able to see some good stuff here, and while that's updating, I'll finish talking about the system a little bit. So again, each of these nodes can update up to 40 megasamples a second at 20 volts peak to peak. We have 8 channels of high-speed data acquisition, again, at 50 megahertz. We can have up to 200 nodes on a common bus, and we synchronize it using RS-422 up to 10 nanoseconds. Everything you see on the front of this plate here is a total of 50 grams. That includes your sensor, data acquisition hardware, your computation, and your memory, and cable and epoxy. Around the other side, the hub weighs 150 grams, and that's everything else you need for the system. The battery here is a 2-kilogram battery, but in normal applications would be hooked up to the 24-volt vehicle power source. Thank you very much.